There are also all of these informal aspects of a conference where, like, we had a gathering of all of the women at the conference last night, and it was really nice, and I made some new friends. So that's the kind of stuff that you would miss if you weren't in person.
Hi everyone. Let's start over. Hi everyone, my name is Ofek. Thank you very much for coming here. We'll spend the next hour or so telling hopefully interesting stories about shared libraries and linkers and some very practical insights and recommendations to top that. Please note I'm not a linker author, so you're very welcome to challenge the views and understanding as I express here. If you do have comments or questions, please note the slide number at the end. First, some terminology. I will use the cross-platform term shared library to refer to what is otherwise known as shared object, dynamic object, DSOs, and in Windows, DLLs or other names. I will try to use the term binary for either an executable or a shared library. I will use the term symbol for either functions or global variables, that is, the variables that the linker and loader need to be aware of. And I will loosely use the term Linux for all Unix descendants. Most of what I'm about to say on Linux holds for macOS too, but I make no guarantees there. Let's start with a nano introduction to linking. A build starts with source files. In the first phase, the compiler processes them into object files. An object file is nothing more than a container for sections. Two canonical examples for sections are text, which contains machine code, and data, which contains program data, but there are countless others. In a second phase, the linker, well, the first thing it does, it pulls together identically named sections from different object files and concatenates them into one larger section. The second thing it does is it reorders the sections so that sections with similar required runtime permissions are adjacent on disk. In a final stage, the loader takes these adjacent chunks called segments and maps them to memory on page-aligned boundaries. And after this mapping, the loader adjusts the page permissions accordingly. For example, code-like pages require read-execute permissions, and so after mapping the code segment, the loader adjusts the permissions to be read and execute. Now, code typically does a lot of function calls. The simplest case being a function call from the binary into itself, but that is not the general case. In general, the process can map shared libraries into its address space and perform calls into functions which are implemented in the shared library. The shared library itself can perform calls into functions implemented in yet other shared libraries. Arguably, the most important job of both the linker and the loader is to properly wire these calls. How might such a wiring look like? Say we have a code that calls the function foo, which is implemented in another binary. The code section itself does not contain the actual string foo. It contains a call instruction into an address that is yet unknown at link time. So the code section contains just a placeholder with a string of zeros. In addition, the linker generates another section called reloc for relocations. On Windows, these are sometimes called fix-ups. And the relocation is essentially a small to-do item for the loader. The linker says, dear loader, please find the function foo, and when you do, overwrite this placeholder with the address you found. Now, this relocation does happen in practice, but it is called a text relocation or direct access relocation, but it is generally frowned upon for two reasons. First, modifying a code section makes the code section unshareable between processes. And second, this form of relocation needs to be done once per call site and not once per function, which can amount to a large difference if you have tens of thousands of calls into the same function. So the more typical scheme is to route all calls to the same function through an indirect call into a single placeholder slot. In this scheme, when the loader reads the relocation, the loader knows it needs to overwrite just a single slot with a function foo's address and not all the call sites. This design trades some runtime performance for hopefully a lot of load time saving. There's an entire section of such placeholders. In Windows, this is called the IAT for import address tables. In Linux, this is a rough approximation for a section known as the GOT, the Global Offset Table, and we will discuss both in some detail soon. Please note already that this design means that cross-binary calls are indirect. They carry the same overhead, at least the same overhead as virtual functions do. And that is not the truth. That is just our first step in our journey towards it. Let's take a closer look at Windows first. A Windows binary contains descriptions of all the imports it consumes in a section called iData, I for import. The most important data structure in an iData section is a directory table. Directory table is a table of entries, one per shared library, one per DLL. Such an entry contains the DLL name, an import lookup table, an offset into a per binary import lookup table, which contains instructions about which symbols to locate within this library, and an offset into an import address table, an IAT, which tells the loader where to write the addresses of these located symbols once they are found. So schematically, what a Windows binary tells the loader is, dear loader, please load the library lib1 and from it locate the symbols F1, F2, and F3. Then load the library lib2 and locate these symbols within it. As we shall see, this is not what happens in Linux. A Linux binary contains not one, but two sections encoding almost identical information to that of the iData in Windows. A dynamic section contains a raw list of library names. And the DINSYM section is the more famous symbol table. It contains not just the symbols to be imported, but all the symbols that this binary contains. The ones to be imported are marked in the symbol table with undefined. They are yet undefined at the time of linking, and it is the responsibility of the loader to find them and wire them properly. So schematically, a Linux binary speaks to the loader in very different terms. It tells the loader, here are the libraries I want you to map into the process, and here's the bucket of symbols that I ask you locate anywhere within these libraries. You can probably see already that even this seemingly benign difference in architecture has some far-reaching implications. A symbol in Linux can be resolved from any of these libraries, the one that you intended it to be or another. On the plus side, this might be intentional behavior. You might have imported some third-party library and you want to override some implementation of a function with your own. This design enables it. And this is an iceberg tip of some much deeper design decisions. Enter interposition. Interposition is the ability of overriding one symbol from another binary, a symbol in one binary from another. And this is a cornerstone of the design of the Linux execution. Now, you might come around alleged motivation for this. There are some statements online that say that the ELF pioneers designed it this way, so shared libraries would mimic the behavior of the earlier static libraries. Supposedly, in static libraries, if several libraries implement the same symbol, then the first definition encountered is used. However, that is not entirely true. It might be the case, but you might also get a linker error complaining about ODR violation. The exact outcome depends on which members are extracted from the static archives. I won't get into that. I have a different conjectured motivation, and that is that the canonical model in the minds of the ELF architects was the library libc. Libc is beyond ubiquitous. It is universal. It is loaded by practically all applications, and it is huge, and therefore it is reasonable to anticipate that users might want to override some of its implementations. And so this capability was baked into the architecture. But this is guesswork. I have no internal knowledge about the motivation. So we discussed one facility which enables interposition, namely the separation of library names from a list of symbols to consume from them. Let's discuss another, library search order. The library search order in Linux is breadth first. What this means is, suppose we have an executable which loads the libraries lib1 and lib2, and these in turn load the libraries lib3, lib4, and lib5. Furthermore, say that lib5 wants to use the symbol foo. The order in which the binaries would be searched by the loader for the symbol foo is first the exe, executable, then lib1, then lib2, then lib3 and 4, and only finally lib5, even if lib5 implements foo. All the other binaries have an opportunity to interpose foo before it is sought in lib5 itself. In particular, the executable is consulted before the current library. This is a default behavior. It can be adjusted. The most direct way is by linking lib5 with the linker switch bsymbolic. Bsymbolic tells the linker that when resolving symbols, undefined symbols in lib5, search in lib5 before the usual breadth first order. Another word needs to be said about preload. LD preload is an environment variable that if it exists and contains a list of library names, they are loaded before the executable, after the executable, but before any of the dependent libraries. And it enters the breadth first search order in this order. Let's sum up this section with a developer-facing implication. Can a shared library symbol be overridden from an executable? In Windows, the answer is no. In Linux, the answer is yes, thanks to interposition. This is exactly what interposition does. By the way, in Mac, the answer is yes, but not by default. Mac Linkers has this capability. It is just not on by default. You need to apply some non-default switch to make it happen. Now, for the first time in this presentation, let's say something about C++. Somewhat surprisingly, C++ does have something to say about interposition. Not in general about interposition, but in a specific niche. Anyone cares to take a guess? Where does C++ and interposition overlap? In the special function new. Here's a quote from the standard on the clause replacement functions. A C++ program may provide the definition for any of the following dynamic memory allocation functions. What follows is a list of flavors of new and delete. And the program's definitions are used instead of the default versions supplied by the implementation. That is what happens on Linux thanks to interposition. That is not what happens on Windows. Windows cannot, never will be able to do that. Strictly speaking, Windows does not conform to this clause of the standard. This is not Windows bashing. Both the Windows design and the Unix design probably predated the standard by many years, but the wording that the standard settled on matches the design of Linux and not Windows. Now, I did start a discussion about this at the ISO mailing list, and I initially suggested to drop this clause altogether. Clearly, it is dead letter. It is not conformed to by a major implementation, and this is not fixable. But a better idea came up on the thread that is linked here. Thiago Maciera suggested, instead of this wording for replacement functions, to have the libraries supply an override hook. Oops, an O was omitted there. The imaginary function set new override would accept some replacement to new to use at runtime, which is not a new idea. This is used in standard in set terminate and set new handler and others. Anyway, this didn't happen yet. I think it's worthy of a paper. Right, let's discuss another mechanism that supports interposition, symbol resolution time. The default behavior is governed by the default switch, allow shlib undefined. If we have this tree of dependencies, and suppose lib5 wishes to import the symbol foo, and the exe wishes to import the symbol bar. The resolution for the exe symbols is checked at link time. The linker would refuse to link the executable if it cannot resolve the symbol bar. That is not true for the libraries. The linker would very happily agree to successfully link lib5 even if it cannot see foo. As far as the linker is concerned, the implementation of foo might lie in the executable, where it has no chance of discovering it. This behavior can be controlled with some switches. The easiest would be linking the executable with no allow shlib undefined, and there are other switches that you can apply to the library to intervene in this behavior. Now let's discuss two developer-facing implications of this. Can we have a process-wide singleton? By singleton, I mean the design pattern, an object which is with a unique instance which is usable by all code in the program. In Windows, the usual implementations of the singleton design pattern would result in a per binary singleton. To form a process-wide singleton that is visible by all binaries in the process, you'd need to have all the binaries in the process link against a single library which implements this singleton and consume it from there. In Linux, you just have to code your singleton and put it in the executable. It would be picked up from there by whichever binary is trying to use it. Here's another interesting one. Can we have circular library dependencies? That is to say, can we have lib1 which uses symbols from lib2, and at the same time, lib2 uses symbols from lib1. In Linux, the answer is yes. You don't have to do anything special for it. Both libraries would be very happy to link with the symbols being undefined at link time and resolved only by the loader. In Windows, the short answer is no. Not by design. You'd have to hack pretty hard to get there. And I need to say that while the Linux design is very convenient, I myself in the past, we worked in a team where we had a very large code base, and we partitioned it to shared libraries semi-arbitrarily, and a ton of circular dependencies ensued, and nobody cared. But despite enjoying this myself, I don't like a design that encourages me to be sloppy. Had we worked on Windows, we would have been forced to invest in properly architecting the layers of our binaries, which is probably better. And here's a quote from a much more knowledgeable person than me, Fanrui Song, aka Musgray. He's the main LLD maintainer today. And he says that allow shlib undefined is an unfortunate default for shared. Changing it, well, it's not feasible, but this is one place where Windows got it right. Okay, this is time to dive into some deeper technical details. Position-independent code. The best way to explain position-independent code is to explain what isn't position-independent. This a call into a fixed hard-coded address is not position-independent. Had this entire binary been loaded at a different address, this baked-in call target would have been invalid. Not only that it is not position-independent, it is not even possible in x64 to call this, well, not in a single instruction. You can't make such a call. Here is another form of a call, a PC relative call. This form of a call, in this form of a call, the target is relative to the current location in the program. This is position independent, but this does not allow for interposition. In this form of a call, the loader has no place to intervene and hijack the implementation of the function. So this is used, but only for what is called hidden symbols, which hopefully we'll have time to discuss later. The default mechanism used to implement position-independent code is through another level of indirection. A call is made indirectly, a call to be position-independent, is being made into a fixed offset into a table of addresses. We already mentioned this table. This is the global offset table. If this entire binary is relocated, then these addresses in the GOT do need to change. This entire binary is not position independent, but the code section is. The proper way to narrate position independent code is position independent code. At runtime, this is the address that would be called indirectly. This is the default implementation in all of your shared libraries, unless you employed some exotic switches. Please note that this has some performance implications. Well, the same performance implications you have for most virtual calls. This toy code, calling f from within G, if you place this code in executable, f would most probably be inlined into G. That is not the case if you put the same code in a shared library. If you put this code in a shared library, the compiler is no longer free to assume that the F implementation that it sees right there is the F implementation that would be used in runtime. Interposition might kick in and preempt this implementation. In particular, inlining is off the table, but even more than that, all attributes that the compiler could have deduced about F are thrown away. All forms of interprocedural optimizations are inhibited. And there's an asterisk here because if you use Clang, Clang does it anyway. Clang designers decided this was too heavy of a price to pay. And that is still not the truth. But hang on, we're getting there. For completeness, I want to, well, I'll mention one detail. If you want to build an executable as position independent, that is a different switch. To build a library as position independent, you have no choice but to use the fpic flag. A shared library would refuse to link otherwise. But to build an executable as position independent, you use a different switch with slightly different semantics. Recall that executable symbols are not interposable. Nothing can preempt them. Nothing comes before the executable in the search order. But in recent decades, the executable is relocatable. Since ASLR hit the scene, executables can be loaded at varying addresses. And to support that, the executable must be built with fpi, position independent executable. Next, let's discuss lazy binding. This is probably the most technically demanding chapter of this talk. Lazy binding is the practice of postponing the resolution of symbol not just to load time, but actually to the first call time. The motivation being that if you have a large binary with tons of symbols, but your particular invocation only uses a few of them, then potentially a lot of resolution work would go to waste. And this can amount to tangible delay in load time that is not necessary. So the ELF designers devised a plot to only resolve what you actually use in the first time. You know, if you type GCC -- version, the responsiveness is amazing. It is immediate. And GCC is one large program consuming, I have no idea how many millions of symbols. This is the way this is achieved, by lazy binding. By default, Linux uses lazy binding. If you do not intervene, symbols in Linux are lazy bound. You can intervene with some compiler switches or at function granularity with a function attribute or with an environment variable. In Windows, by default, lazy binding is off. In Windows lingo, this is called delay load. And to enjoy it, you need to specify after the delay load switch the list of DLLs you want to lazy bind to. There is an important asterisk here on this yes, and we will return to it later. So recall that this is where we left off in our pursuit after the true flow of a call in Linux. And to understand lazy binding, let's take a closer look at it. To have lazy binding, obviously the address of the function in the got slot would have to change in runtime. initially the address here would have to route the execution into someone that performs the actual resolution, and this someone would have to overwrite the address with the resolved address of f. So this is how this is achieved. The call is in fact not an indirect call into the GOT slot. It is a direct call into a procedure lookup stub. I don't know if this is an official name. This is just the name that I chose. This stub starts with an indirect jump to the GOT slot. As said initially, this slot contains the address of somewhere that performs the resolution. And incidentally, this somewhere is exactly the next instruction in the stub. So on first call, this jumps exactly to the next instruction. This next instruction sets up the argument to the resolver and calls the resolver. The resolver is part of the loader, which is a different binary that is still loaded into the process address space. This resolver performs the resolution, does its magic, locates the function, and overwrites the GOT slot with the address it found. Let's not forget that after all this, we must delegate the execution to f itself. After all, this was part of an f call. And this is how the first call to a function which is lazily bound looks like. After the first call, things are much simpler. The indirect jump from the first instruction in the stub jumps directly to f. Now, that was an individual procedure lookup stub. The full table of all such stubs is called the procedure lookup table, or PLT. There's a good chance you came across this term already. And that is as close as we'd get to the full truth in this talk. There are some extra details here that I think I won't get into. Okay. An interesting wrinkle comes up when we consider function pointers. Here's another quote from the standard. When we're comparing two pointers, if the pointers are both null, both point to the same function, or both represent the same address, they compare equal. Now, when I first came across this, it struck me as odd that this even needs to be said. I mean, of course, that if they point to the same function, they need to be equal. But after learning about the PLT and GOT design, it seems like magic that this is even possible. The actual calls are made into PLT slots, and a PLT is per binary. Calls in different binaries are actually routed to different PLTs. How can function pointers in different binaries compare equal? Well, Linux sweats quite a bit to get this done. What happens is that in a state where an executable and the library both reference f and say the library takes its address, the address is actually stored in the symbol table of the executable as the value of the symbol f. When the loader needs to resolve the address of f here, it actually takes it from the symbol table in the executable. This way, both the executable and lib1 would get the same address for f, and in fact, it would be a valid function pointer. Invoking this would result in the invocation of f. This is not comprehensive. This was a too brief explanation about just one case. The behavior is different for executables built with Pi, and the behavior is different for a comparison between two libs and not an executable and a lib. And actually the spec, the system V ABI, did not chase after all these variants and implementation. But the important point is that Linux tries very hard. Even today, this is a link to a commit from a few months ago that fixes some corner case in exactly this, and a comparison of function pointers taken from different binaries. I'm sorry to say that Windows doesn't even try. In Windows, say I marked some DLL as delay load, and I print the address before and after calling this function, I get two different addresses. The first address is the address of the resolution stub, and the second address is the address of the real function. It needs to be said, one, in Windows, delay load is not the default. And two, a case can be made that in the presence of non-default build switches, standard conformance is, well, I don't know what to say about it. There are build switches that are known to intentionally make the resulting binary non-conforming. Short summary so far. What do we have? As a rough approximation, the global offset table is in place to support interposition. The procedure lookup table is there to support lazy binding. Both of these design goals are highly questionable today. Let's start with interposition. Interposition first has an uneasy coexistence with C++ ODR. It de facto enables the coexistence of more than one implementation to a function in a program. It is, I think it is rarely used, but I actually would like your input. Did anyone ever use interposition? Yes, you did? I'll be very curious to hear about what? In preload? To override an implementation? I'm actually curious. I used preload too, but not for interposition. I'm curious to hear about your use case later. So that's a, sorry?
The standard case is JMalloc and LD preload.
Yeah, the standard case is something like new, which I mentioned. Yes, that's true.
And also OpenGL debugging. There's OpenGL debuggers put in place.
I didn't think of that. I didn't. That's interesting. Thank you. So that was 3 out of a room of maybe 100, 4.
So the problem is the alternative to interposition on Windows is terrible.
Yes. Yes. There are indications to say that it is doubtful whether this design would have taken today, even though we see that there is some usage. I'm curious to hear more. Here's one quote from a recent GCC discussion. Outside of ELF, the world is shifting to a direct binding and non-interposition. And regarding the performance implication, here's one interesting data point. CPython, a few years ago, started building with no semantic interposition, essentially blocking interposition, and got a 1.3x speedup. That's one data point, but I don't think it's an outlier. Interposition does take a very tangible toll, even if you don't use it. Next, let's discuss, in retrospect, lazy binding. This is the asterisk that I said I would get back to. I said that in Linux, lazy binding is on by default, but a lot of people are unhappy with that today. The apparatus, as described, requires that the global offset table remains writable throughout the program execution. This is a glaring security hole. There are actually attacks in the wild that this is a hacker bonanza. You just need to modify 4 bytes, I don't know how many bytes, in a specific location, and you can easily write execution to wherever you want. So as of today, the linker still defaults to -z lazy, that is lazy binding, but many, I don't dare say most, but many major distros configure the compiler so that the compiler driver would invoke the linker with the switch -z relrow. Relrow stands for relocate and read-only. What this does is the PLT is still in place, but relocations are performed eagerly at load time, after which the loader makes the GOT read-only. And I know that other languages, Zig and Rust, do this too. In Zig and Rust, this is not a per distro decision. Zig and Rust decided to build with Z Railroad. And it seems kind of weird that we still erect this magnificent structure of the PLT to support lazy loading, then resolve everything eagerly. Hopefully this design still can be looked into in the future. Yes, we still have time, and I want to say a few words about symbol visibility, which is an important topic. On Windows, symbol visibility is simple. We can decorate a symbol as declspec DLL export, which means that the symbol is added to the e-data, export data section, and is visible by other binaries. You can also declare a symbol as DLL import. This is not the act that adds it to the iData section. That's achieved by statically linking an import library, and I won't discuss this further. But the important point is that most symbols are neither exported nor imported. Most symbols are internal to the binary. In Linux, things are considerably more complex. A binary has a symbol table which contains all symbols and is always visible to other binaries. I shouldn't have said it contains all symbols. It contains all global symbols in the binary. And so these symbols are potentially exported if other binaries select to refer to them. In the symbol table, symbols can be marked as undefined, which forces the loader to import them. But this is not the end of the story. There is another axis of visibility for symbols in Linux, and that is explicit visibility attribute. Symbols can have default visibility, protected visibility, or hidden visibility. There is also something called it internal, but as of today it is a no-op. The reason you might care about visibility is this thing I said earlier. This form of PC relative call is used only for hidden symbols, and this longer PLT GOT route is taken for default visibility symbols. So a default visibility symbol is available to other binaries, subject to interposition, and appears in the GOT and in the symbol table. A hidden symbol is none of those. A protected symbol is just like a default symbol, except it is not subject to interposition. So by default, all your symbols go through the longer route of PLT and GOT to be used, unlike Windows, where the default is analogous to hidden. I'd like to read this quote verbatim. Using F visibility equals hidden, making all symbols hidden by default, can very substantially improve linking and load times of shared object libraries, produce more optimized code, provide near-perfect API export, and prevent symbol clashes. It is strongly recommended that you use this in any shared objects you distribute. Does anyone know where this quote is from? This is from the GCC man page. This is as close as it gets to officially saying we got the defaults wrong. So the burden is on us, on developers, to not stick with the defaults. If we apply this switch, F visibility equals hidden, then by default, all symbols in a binary would be hidden, and only those symbols that we would decorate with attribute visibility default would have default visibility, would be visible externally. There are other switches here that I mentioned for completeness, and I urge you to explore, but I won't discuss here. I won't discuss this either. I want to leave time for questions. So some practical recommendations if you're building shared libraries on Linux. Opt out of interposition. Build with F visibility hidden and be symbolic. Mark only the symbols that are the external interfaces to your library with attribute visibility protected. Protected and not default to make them not subject to interposition. There are some easier fallbacks with less manual work that I encourage you to explore. And essentially what I'm asking of you is to link more like Windows. The last thing that I want to say is a preemptive answer to a thought that no doubt has occurred to many of you. What's the knee-jerk response when someone tries to discuss with you C++ and shared libraries? Sorry? No, I'm sorry, I can't hear you. Yeah, but I mean, suppose that shared libraries is part of the discussion. What I was aiming at is that almost always when I try to discuss it, the first statement that I hear is shared libraries are outside of scope of C++. And so there's not much point in discussing shared libraries and its impact on the C++ standard. While it is true, I think this doesn't mean what most people think it means. This doesn't mean that writing code into shared library makes it undefined behavior, or that consuming shared libraries makes it undefined behavior, or that the standard is applicable only in some imaginary world where shared libraries do not exist. Hopefully that is not the situation. I'll shamelessly steal this quote from an ISO mailing list thread that I started. Shared libraries are in fact outside the scope for C++, but in the same way that x64 instruction encoding is outside of the scope. This is just an implementation detail. It is a low-level concern, and it's up to the platform to make a conforming C++ implementation on top of that stuff. you're welcome to join this discussion. So, to sum up some takeaways that I hope to leave you with, Linux and Windows designs are fundamentally very different. The Linux design is burdened by slightly out-of-date design goals. Some practical recommendations: if you work in Linux, please link with visibility hidden and be symbolic. Shared libraries are outside the scope of the standard is not a valid bailout if you get involved in C++ discussions around these matters. And you know, when I started learning about linkers, trying to make sense of it all, I was under the impression that linkers are like a solved problem. They are boring little programs that do mundane wiring. That is very far from the truth. Linkers are very messy. They are very creative and wonderful. And the linker repos are very, very active today. Things are still changing. That's all I had to say. The best way to reach me is either by mail or LinkedIn. We still have 8.5 minutes in which I'll be happy to take questions. Thank you very much. If you have questions, please step up to the mic.
Nowadays, linkers are no longer invoked by people directly. We all use build systems.
Yes.
Are you aware of build systems that basically fix these defaults for you by default?
Excellent question. No, I have no idea. If anyone is involved with such systems, and this is a very interesting hook to try and intervene in, to try to make the world a better place. Thank you. Yes.
First of all, thank you for the presentation. I wanted to ask whether can you discuss a bit about the cost of this indirect calls to functions?
Yes. This is a hot topic. In fact, there's a presentation this Friday by Shachar Shemesh, I think, on this very topic. What is the true overhead of virtual function calls? And I believe he submits that the overhead is negligible. I can add here. Yes, I can add here one data point to the contrary. I can say that compiler authors are still investing heavily in devirtualizing calls. To try to take virtual calls, deduce their exact target, and make the call non-virtually. And there is, in this work, they report a maximum speedup of 30%, but an average speedup of 0.8%. So maybe 1% is the good rule of thumb to keep in mind. And these are benchmarks on real large programs, not on toy snippets that just make many iterations of small calls. So while 1% isn't a lot, it is certainly not negligible. This is something that I would hate to pay for interposition and design that I don't really use. Yes, please.
Could you comment on the use of DL open? Is the process basically the same as what you get automatically?
Yes.
So all the flag recommendations you have would apply, right?
Yes. For example, I can say for certainty that if you DL open a library that was built with bsymbolic, then the search order in its dependencies would indeed search this library first. What other flags are you asking about?
No, just the flags you were talking
Hidden, yeah, absolutely. Yes, you don't get a visibility into the symbol table of a library. You don't get different visibility just because you loaded it dynamically. Yes. Go ahead.
Again, thank you for the presentation. I'm very happy to see a single place where like it's all back together. Do you have the version of the presentation covering also Mac architecture from Mac, and maybe like more details, like things like our path are like completely out of scope for now. I guess you're limited by time, but it's like looks like a very logical missing piece of your presentation. Do you have like a full version of it?
I did take out a discussion of RPath. You were asking about RPath specifically? Yes, this is one of the many things that I had to take out. I did not intend, even initially, to discuss Mac. I have no direct experience with Mac, I'm afraid. I can say, just a second. Yes. I can say that there is a 4-day workshop on shared libraries delivered by Michael Karisk. Michael Karisk was until recently the owner of the Linux Man pages. I did not take this workshop, but I took another workshop of Michael, and I'm sure this one is great too. He won't be giving it this year because there wasn't enough interest, but maybe we can change that now. If he does give it this year, then I would join you.
And the final, are you going to share your presentation somewhere publicly or not?
Yes, I put it in the Discord channel for this talk, right before coming here.
Thank you.
Sure.
Thank you for the talk. This is a very practical question. What do you have in terms of recommendations for people who would like to use C++23 today and need to deploy their applications to, let's say, older OS versions, which might not have that the standard library available, or maybe even an older one?
I actually did something similar. We built our application with a lot of embedded RPath directives, which would route the search for standard libraries into libraries of our control. And then we deployed our application with these libraries to rather old machines with Ubuntu 14. And it is rather delicate. For one, you'd probably want to customize dynamic linker. Probably have to build with a dynamic linker switch and specify it explicitly and route it to the folder that you deploy. Mm-hmm. There are other traps to be aware of there, but it is doable. I did it, but I'm not aware of any particular pitfalls regarding shared libraries in this task.
Okay, and so you would also go as deep as the C library, or
sorry, come again?
Would you also embed the C library, or just the C++
We
standard
didn't
library?
do this. We didn't link statically, if that's what you're asking.
Okay.
If you're able to link statically, then this is probably the least friction route.
Uh-huh.
We weren't able to for various reasons.
Thank you very much.
Sure. Yes? Okay. Right on time. Thank you very much.